Frontiers of Science lecture of the academic year. On behalf of Darrell Butt, from the Dean of the College of Mines and Earth Sciences, and myself, Henry White, I'm the Dean of the College of Science. We are just feel wonderful that so many people have come out to hear this lecture about books, very special books. This is a little different from Frontiers of Science, where we're generally talking about what's the newest thing happening in science and in engineering. But this is going to be a wonderful lecture. For the newcomers here tonight, Frontiers of Science is the longest running lecture at the University of Utah. We just celebrated our 50th anniversary in the spring. Professor Doone Gibbs from physics, former professor, founded this lecture, and he was able to attend last spring and join in the celebration. So we're starting tonight the next 50 years, the next half century with this presentation. We're off to the races here. So the topic of our presentation tonight is monumental scientific achievements communicated through the centuries in wonderful books, wonderful and very rare books that you will learn and see tonight are located over in the Marriott Library. And since I mentioned the Marriott Library, let me pause and point out, recognize a special guest here. My dear friend and the Dean and University Librarian, Alberta Comer, please stand up and be recognized. The Marriott Library is wonderful. We're going to hear maybe, some of this will probably be new to you, hearing about the rare books collection, the special collection. But there's so many wonderful things going over there in the library, all the programs that support research and education at the university. So you do a wonderful job and your staff, so congratulations. Okay, so let me tell you about my experience with rare books here at the university. So about 15, 18 years ago, I was working on a problem trying to understand electrical conduction in nanoporous materials. That means nothing to you guys. And I was trying to find a mathematical solution to a physical problem, a description, just an equation describing what we were measuring so I could write up a manuscript. And I asked everybody, and nobody could tell me who had solved that problem. And finally, someone on the East Coast said, Maxwell did, James Clerk Maxwell, 1873. You'll find it in the treatise on electricity and magnetism. And I got on the internet, went over to the Marriott page, and I thought, you know, I'm out in the desert. I was new to Utah, I was out in the desert, and I thought, they're never going to have this, right? And I looked it up, and there it was, Maxwell, 1873, rare books collection. And I went over there, and I asked for a copy. I didn't know how it worked. And filled out a piece of paper, and staff person went in the back, and 15 minutes later, they came back through the door and gave me Maxwell, 1873. And I was so excited about getting the solution to that problem for my research, I didn't even notice the book. And I gave the book back. I was overjoyed with my problem being solved. I gave the book back, and the staff person took it back through that door. And it never occurred for me to ask, what else do you have behind that door? So last year, a few of us had the pleasure of being invited to an event at the Marriott Library where tonight's speaker, Louise Poulton, also gave a lecture. And I recall it was a beautiful lecture on the joy of holding and reading a book. It was just wonderful. And before the lecture, she and the staff had spread out a few examples of the rare books from their collection. And I was the first one in line. I don't know if you remember that. And I was walking around when you were telling me about the books, and boom, 1789, Lavoisier's book on chemistry. That is the turning point in the history of chemistry when that book was published. Before that we were all alchemists. And after that book was published, we were all chemists. And things worked. And I just went, holy cow. And then I asked the big question, what else do you have? And you told me. And I came back. I was really intimidated. I wanted to go see these books. So what I did is the next week, I sent an email to my partner in crime, the nerdiest, geekiest scientist on campus that I know, Ben Bromley, who's chair professor. If you know Ben, you know what I'm talking about. And that's a compliment to Ben, right? And I said, Ben, she's got Newton over there locked up. First editions. Remember this? I said, you want to go? And you said, yes, right? So we went over and we spent an hour or two touring your facility, browsing shelves, Darwin, Kepler, opening a little book by Kepler, folding out these figures showing comets going through the solar system. And that must have been 17 something, I can't remember. And it was just absolutely wonderful. It was just incredible. And we just went, and we got the narrative from Louise as we went. She told the story about the books. And it was one of the best 2 hours I've had in the last 25 years at the campus at the University of Utah. Okay. So, the most important things that these books represent, or what they contain, are the laws and the rules of science and math that we all use every day. All right? Modern medicine, iPhones don't exist without those books and the knowledge. All right? And that's really important when you listen to Louise tonight. Keep that in mind. Keep it all in perspective. Everything you need, all the scientific principles, every single one of them, are contained in that 1873 book by Maxwell. There's nothing new except some routine engineering to make an iPhone. And I kid you not. Ben will vouch for that, right? Okay, of lesser importance, I'm going to get in trouble here. Of lesser importance, at least to scientists, geeky scientists like Ben and me, but of importance to historians and people in the humanities. But of equal beauty are the intimate stories that these books tell about the progress of science. When you read these books, you see how scientists really struggled to come up with ideas that we just accept as secondhand. And when you take a course in physics, I remember this as an undergraduate, and it hasn't changed, I'm sure. You take a course in physics and you open chapter 5, the first page of chapter 5 will be Newton's second law, and it will just simply say F equals ma, right? But F equals ma, getting to that equation is a book that thick, and 40 years of hard work. And when you go and look at these books that Louise in the library has, you truly appreciate the magnitude of these discoveries. Okay, the books, I tell you, the other thing I'm going to end with here is the books, whenever I pick up an old scientific book, I love these books, and I pick them up and I read them, I always end up laughing at how ridiculous some of the concepts are. They were so wrong at times. And the one that Ben and I enjoyed when we were over that day, I think it was Newton's book on optics, called Optics. It's got a longer title, but it is Optics. And the foreword written by Newton, the foreword to this book, which changed science, he just goes on and on about how Leibniz plagiarizes his invention of calculus. And nothing's changed. I was an editor for 15 years for a chemistry journal, and I've seen those same statements in letters written to me. And I can tell you, what's really funny, we think of Newton as this god of science, and then you read this, and it just goes on, and he was very spiteful, very insecure, really obnoxious, and tearing this other mathematician apart, right? And it made me laugh. I shouldn't laugh at that, But it just shows how human, I mean, we're all the same. 400 years have gone by, and at least on that front, nothing has changed. Okay, let me tell you about the speaker. Louise Poulton, Managing Curator of the Rare Books Collection at the Marriott Library. Louise has a BA in History from the University of Utah, and she's been with the Marriott Library for nearly a quarter of a century. In her role as the Managing Curator of Rare Books, she works with faculty across all disciplines, not just science, all disciplines, in getting these books into the classrooms and making students aware of the history of whatever they're studying. It must be a wonderful job, okay? And I'm going to end, I read her bio, I read a bio statement here, and I may preempt, you may want to say this yourself, but I'm going to say it. So she's often asked, what is her favorite book? And it's a question she will not answer for fear of making all the other books cry. Louise, thank you so much for doing this. Come on up.
Hi. It's really nice to see you all here. All right. Well, here we go. I have the great privilege of working with the rare book collections at the J. Willard Marriott Library. And the very best part of my job is putting these books into your hands, students, faculty, and community. We have a collection of about 80,000 pieces, and we brought 40 of these books here for you to hold tonight after the lecture. I'm going to try to convince you that these books, made possible by the greatest technological innovation in Western history, help us understand the conversation, collaboration, and controversy that scientists have been having with each other and with the rest of us for the past 500 years. We know that knowledge is not created in a vacuum. Data is one thing. The collection and dissemination of data is another. I propose that the printing press, developed in Germany by Johannes Gutenberg nearly 600 years ago, and the printers who operated the variations of this contraption over the centuries, played an important role in the creation of knowledge, that the product and process of printing is just as important as the data it reports and stores. So let's begin with the printing of a book written 2,000 years before Gutenberg was born. Euclid was a Greek mathematician who compiled a textbook around 300 BCE that is still in use today. In 1482, 32 years after the first book, the Bible, was printed by Johannes Gutenberg using movable type, Erhard Rotdolt, a German printer in Venice, worked out a way to print the geometrical diagrams necessary to this book's success, diagrams that elucidate the text. Elements of Geometry is the first printed book to contain geometrical figures, more than 420 marginal diagrams. Beyond these little gems, the book is designed to please the eye of the beholder. An elegant three-sided vine-style woodcut announces in typical preprint manuscript fashion the start of what's to come. Several hundred small ornamental capitals announce new theorems. The page layout puts the reader on par with the author. The page begins a conversation between reader and writer. The printer is leading the conversation with great consideration for both. We will see this kind of aesthetic thoughtfulness for the presentation of ideas many times tonight. It is a remarkable part of the books that introduced the world to new and dramatic ideas. This is the drama of the messenger itself. In his dedication, Rotdolt suggested that the scarcity of printed mathematical works was due to the problems involved in printing the diagrams. He then happily announced that he had discovered a method of printing them as easily as the text. He did not elaborate upon the method. That would have been revealing a trade secret. But he does tell the reader to be assured that books bought from his press would be of the finest quality aesthetically and editorially. Now, we might assume from this that science was influenced by newfangled printing and vice versa. Here is another book from Rotdold's press, also printed in 1482, that suggests just such a thing. Regiomontanus printed Calendarium at his own press in Nuremberg in 1471. Rotdold printed it in Venice in 1476 and again in 1482. Regiomontanus was one of the great Renaissance figures in mathematics and astronomy. He was one of the first publishers of astronomical material. This book represents an early application of modern scientific methods of calculations and observations to the problems of the lunar calendar and the accurate prediction of eclipses. The last 2 pages are printed on 4 pages of thick paper, pasted together to form astronomical instruments. This edition is an example of the technical skill that Rotdold, the printer, had in overcoming the challenges of creating instruments as part of revealing scientific information. And once again, Rotdold produced this information artfully. The title page initial is printed in red. Printing in 2 colors at this time was no small technical feat, and bordered with intricate decoration. Woodcut initials are printed throughout the book. As beautiful and as intriguing as these books are, printing does not initially seem to have played much of a part in developing scientific theory. Humanist scholars were principally concerned with rescuing and restoring the texts of classical theorists, like Ptolemy, for example. Renaissance rediscovery of the Greeks and the printing of these texts enhanced and reinforced the prestige of ancient wisdom. In fact, Regiomontanus had much to do with the resurrection of the influence of Ptolemy. But the availability of multiple copies made possible by printing may have helped draw public attention to science and sustain that interest in a way that had not happened before. Tycho Brahe, nearly 100 years after this book was printed, used this work by Regiomontanus. Copernicus also used the work of Regiomontanus. Regiomontanus was ambitious. He printed a list of works that were to come from his press, but he died that same year, in 1474. Just his list, however, guided the publication programs of others and gave 16th century astronomers a bibliographic tool. What should I read? Tycho Brahe studied Ptolemy and Regiomontanus and Copernicus. He found contradictory predictions concerning the conjunction of planets, which compelled him to study the skies for himself. And from those studies, he added fresh data to current and past conversations. And in the same way, Johann Kepler studied and added to the work of Brahe. But we are, as science tends to do, getting ahead of ourselves. Aldus Manutius, another master printer in Venice, published a collection of the basic works of the ancient astronomers and geographers. Aldus, too, prided himself in the work of his press. His books, like those of Rotdold before him, were designed to please the reader, to be read. Clear typography and simple yet dramatic design elements that kept the eye moving from the end of one chapter to the beginning of the next. The Aldine Press published ancient works in Latin and Greek. Aldus Manutius cut and designed the first complete font of the Greek alphabet. Greek was the language of Strabo. Strabo's Geographia was one of the first works from antiquity to collect all the geographical knowledge at the time. Until Ptolemy, unlike Ptolemy, who studied cartography and applied mathematics and geometry to understanding the shape and size of land and sea, Strabo had a more descriptive and anthropological approach, giving a sketch of the physical peculiarities, the natural productions of a country, the customs and institutions of its people, and thereby much valuable information on ethnology and trade. This information was meant for the statesman, but it was science nonetheless. It was, in fact, an explicit affirmation of the superiority of knowledge derived by observation. Early Renaissance scholars and printers were careful not to challenge the authority of the Roman Catholic Church and to seek the approval of the crown. Later scholars and printers became less wary of that authority, and we shall talk about what happened to them soon. Renaissance scholars studied ancient Greek and Roman texts, and also medieval Arabic texts. Translations of Arabic works in Latin appeared in several editions within the first 50 years of printing. This is the first printed work in Arabic of Avicenna, Ibn Sina, a Persian scientist who lived in the 11th century. The Medici press in Rome developed the first Arabic font. In an age of discovery, it made sense to read works in their original language. In the 11th century, Avicenna introduced the works of Aristotle to the Arabs, but Avicenna also thought for himself. His encyclopedic work, Al-Shifa, is divided into 4 parts: logic, mathematics, physics, and metaphysics, lest we forget the soul. In the late 15th and early 16th centuries, the astronomy, geography, physics, natural history, and mathematics of the ancient and the medieval world became available to nearly anyone who wanted to read them in their original language and in translation. With the help of the printing press and its operators, it was possible to reinterpret, comment upon, and add to the teachings of the classical scientists. But even with the printing press, many classical and medieval texts languished in single manuscript form. Many early printers may have been friendly to scholarship, but printing was, after all, a livelihood. First and foremost, the customer base for scientific works was rather limited. Reinterpretations, commentary, and additions to the classics often went unpublished in the early print era of the scientific exchange of ideas. 50 years after this edition of Avicenna in Arabic was printed, 50 years before this edition of Avicenna in Arabic was printed, Copernicus published the results of his researches to little public interest, and it was not printed again for another 23 years. During the Renaissance, then, as now, medicine, however primitive, was of primary interest. Medical treatments were based on botany, but herbals copied and recopied for millennia often misidentified plants. This 7th century manuscript is a copy of a pharmacological treatise written by the Greek physician Paidonius Dioscorides in the 1st century. More than 400 plants are described in this herbal manual. The work was used by the medieval world for centuries. In the 6th century, it was translated into Latin. By the 9th century, it had been translated into Arabic and Hebrew. And as we can see here, even if we don't know that this image is supposed to be of a mandrake or what a mandrake is, the drawings are less than accurate. Early printing became most useful for the less abstract sciences like botany and anatomy. In these instances, illustration became the key to capturing and expressing new information. This herbal established a new standard of scientific observation and accurate illustration. While its author, Leonhard Fuchs, compiled his text from various classical sources, including Dioscorides, he added his own field observations. He identified the plants in Latin, Greek, and German, and he worked with trained artists. So important to Fuchs was the detailed woodcuts that he praised the artists in his preface and honored them further with their portraits and depictions of the tools of their trade at the back of the book. Fuchs's book contained the first published illustrations of plants from the Americas. Here, the pumpkin, but also the marigold, maize, the potato, and tobacco, all introduced to Europe as a consequence of the Columbian encounter. By the 16th century, with increased global travel and the new tools of new techniques of drawing and perspective, botanists stopped relying on the ancients and turned to direct observation. Illustration played a crucial role in expanding knowledge. Real progress in botanical description was possible only when scholars had access to realistic illustrations. Other scholars followed this example of the importance of accurate image to go along with complex ideas. The fact of the matter is that classical authors warned against trusting what were then, of course, hand-copied books, and especially hand-copied pictures. Early readers, lacking plant guides or birdwatchers' manuals, could not discriminate between a fanciful or a factual rendering. Johann Fuchs and Georg Agricola had fresh drawings of their subjects prepared. Agricola's work on mineralogy was first published in Latin in Basel in 1546. The copy here is the first Italian edition, printed in Venice in 1550. Agricola rather sneered at the misinformation derived from ancient manuscripts. Fair enough, perhaps, but medieval natural philosophers did not lack in curiosity about the world. Their manuscripts, albeit primitive, provided evidence of, well, something, and a basis, a foundation from which to move forward. Agricola and his contemporaries had access to secondhand information that had been compiled over the course of many generations. They did have something to work with. What the, what the ancients left to 16th century scholars may not have been comprehensive or a uniform picture of the world, but the numerous incongruous images and descriptions left to them over the centuries were, because of the printing press, duplicated in quantities that brought the information in contact with far more people than ever before. The information, faulty as it may have been, could now be compared and contrasted. Agricola was a German scholar and a devout Catholic who spent many years in Italy during the Reformation conflicts in his homeland. For a time, he worked for printer Aldus Manutius in Venice. Agricola's work on mineralogy is written in the form of a dialogue between two medical students and a miner and a foundry clerk. The lively discussion focuses on ore deposits, silver mines, ancient mining, and the use of minerals for medical purposes. It is the first attempt to give the practical work of mining a semblance of scientific order. In 1546, Agricola's work provided the first scientific classification of minerals. He classified his minerals on the basis of geometric forms such as spheres, cones, or plates. This book is an example of the large-scale data collection, an intermittent and limited enterprise in the manuscript era that had now become continuous and ever-expanding. With the advent of print and multiple copies of the same text available over a wider area to many people all at once, cross-referencing was possible, a phenomenon nearly impossible before. A large library is as much a scientific instrument as a telescope and offers a flow of information that makes conversation a fact, not a wish. Guillaume Rondelet was one of the first of 16th century scientists to break with the 1800-year-old tradition among natural historians of relying on Aristotle's understanding of animals. and to begin the practice of gathering and reporting firsthand information. In this book, Rondelet documents his observations on fresh fish, fresh water, and marine life. Rondelet reports anatomical form and compound structure of aquatic organisms and relates this to biological functions. This is a perfect example of the growing attitude of science in the 16th century, an empirical methodology placing observation and investigation above rumination. Although we can certainly wonder, what is that? Rondelet's book on fish was first printed in 1551 in Latin, as was proper to any scholarly endeavor of the time, and then in French in 1558. The wood engravings are superb renditions. Rondelet's book enjoyed popular success. It also serves as a way to remark on some of the innovations in the formatting of the book itself that blossomed in this period and helped the flow of the conversation. An index of sorts was used in some medieval manuscripts, but it was an occasional and somewhat haphazard feature of those and of early printed books. In the 16th century, it became increasingly systematic and a standard element of scholarly texts. The index was rationalized by being alphabetized. Just this device alone meant an evolving conversation between the author, the printer, and the reader. This was give and take of the highest order. Give information and make it discoverable with bibliographic tools for use by the reading and researching public. The compiling and publication of dictionaries became a fast-growing industry. The increased output of these and other rudimentary bibliographic aids like title pages and book lists enabled a search of literature, a lit review, on a scale not possible in the manuscript and early print eras. Profit-seeking printers and the collaboration among scattered observers made possible by multiple books helped accelerate data collection and push it along new paths. The influx of data meant that scientists had to use this indispensable and now available information to work things out. Comparison of all the observations of previous writers with one's own observations was possible on a scale impossible before. The work of previous observers, now recorded and available, meant that contemporary readers could confirm or refute these observations. 16th century readers could compare 2, 3, or more theories, sets of computations, observations. A century earlier, students were fortunate to have access to one theory. These multiple theories did not have to be copied and memorized. Less reliance on memory and rote repetition meant that intellectual labor could move elsewhere. Oops, we're not there yet. With multiple works of old and a growing base of new information, anomalies in old records could be detected, information could be more precisely pinpointed, collaborators from multiple regions could be enlisted, and each fresh observation put into a permanent form, making corrections in successive editions possible. Of course, all of this was affected by the same things that still interrupt scholarly and scientific pursuits today: disease, personal problems, supply of materials, war, politics. And while printing had its distinct advantages for science, it was a lot of work. Punch-cutting new symbols, setting type, these were issues when Erhard Rotdolt printed Euclid's Elements and continued to be, in fact, still are. And then there is the necessity of marketing. Printing and publication encourages self-advertisement. Just as Rotdolt used the page before his incipit to advertise himself and his product, authors now had to make some kind of personal pitch for the worthiness of their theories, and publishers had to find ways to entice buyers. There was, with multiple copies of multiple works being offered at book fairs and on the streets, a larger reading public, a larger pool of potential buyers, and a larger pool of potential observers. Authors of herbals, for instance, would call upon their readers to send in notes about plants. This encouraged reading and made the reader feel as if he or she were part of the process, and it's an early form of crowdsourcing, data collection on a scale never imagined, let alone possible before. The same year that Copernicus published his heliocentric theory of the structure of the universe, the physician to Charles V published a book like no other. Andreas Vesalius's Anatomy became one of the most influential books in the history of science. His detailed illustrations were important not only for their precision, but for demonstrating the pivotal principle of linear perspective. Artists from the school of Titian created drawings for the woodcuts. Vesalius's book demonstrated the importance of working with the printer to offer a quality product. Vesalius was unhappy with the first edition, and 12 years later released this, the second edition, in 1555. And here, in the midst of many faces, there he is. Here in the midst of many faces, in that necessary act of self-promotion, Vesalius stares out at the reader and he tells us, pay attention. This is different. This is important, and you need to read this. Our eye zeroes in on Vesalius because of that linear perspective. There is something else depicted here that was meant to stun the viewer and would have done exactly that in 1543. Vesalius, the great physician, is getting his hands dirty. The job of actually touching the human body for the purpose of understanding it, let alone healing it, was left to others before this. Barbers were famously surgeons. Vesalius admonished his colleagues and fellow scholars to get their hands dirty. Working closely with the publisher was yet another way Vesalius got his hands dirty. The illustrations in his book relate precisely to the text and are laid out with a precision that is worthy of imitation today. The sequence of illustration from skeleton to various muscle layers and nerves succeeded in interpreting the human body to a degree never before achieved. Vesalius added to the second edition corrections and new information. The woodcut impressions of the second edition are clearer than those of the first. The press work is finer, and the quality of the paper is better. Vesalius's recourse to pictorial statements to back up his text gave meaning to it in any language. Words can be ambiguous. This work, written in Latin, was constantly reissued, copied, imitated. Through the medium of the engravings, the human anatomical structure became widely, not to mention better, understood. Image to word, word to image, printing reduced translation problems and helped to set the stage for the rise of modern science. The revolution took place as authors, in despair of the inadequacies of purely verbal description, sought the aid of skilled draftsmen and artists, trained as part of their craft to observe carefully and well. Still, in many fields in the 16th century saw no significant advances in scientific understanding. This began to change at the beginning of the 17th century. The botanical and anatomical treatises of Fuchs and Vesalius could only be undertaken by a well-staffed, well-stocked, well-connected printing firm. Most works of this type came from a handful of cities that between them shaped the book market: Paris, Lyon, and Antwerp, Venice, Basel, Frankfurt, and Nuremberg. The publication of serious works of investigative scholarship required a particular sort of printer. These milestones of scientific investigation were large and complex and meant for a widely dispersed international readership. In the 17th century, less expensive, smaller books like this one by Johannes Kepler, published in 1604, meant that a sustained program of even wider dissemination could take place. With this little unassuming book, Kepler's work began to dominate cosmological science. This is Kepler's work on optics, something he became interested in after he observed a partial solar eclipse in 1600. He made a pinhole viewer through which he took measurements that suggested that the moon's diameter was less than that of the sun. Who knew? With his observations, Kepler defined the concept of the light ray. This work begins with a treatise on vision and the human eye, demonstrating how the retina is essential to sight and the part the lens plays in refraction. It contains the first correct physiological explanation of the defects of sight. And I am grateful just for that. In the second part, Kepler discusses the instrumentation he used for his observations. The theories in this work eventually changed the course of the study of optics. Big things can come in small packages. 15 years later, Kepler published his work on comets. Divided into 3 sections, Kepler wrote of his observations of the comets of 1607 and 1618. Edmund Halley, at the end of the 17th century, used Kepler's observations and computations in conjunction with his own observations of a comet's passage in 1682. So here it is, the conversation. Just some guys standing on a street corner talking. But of course, no group of people talking is as simple or as innocent as just that. Agricola, a Catholic, and Kepler, a Protestant, faced persecution. So did just about everyone else in the 16th and 17th centuries. Religious persecution, political persecution. Not only was the technology of printing complicated and expensive, but so were the ideas made possible in the print era. Authors were imperiled, but so were printers. And when publication outlets are imperiled, so is speculative freedom. Official censorship affected published pieces and pieces that were not yet published. Descartes stopped working on his cosmological treatise when he heard of Galileo's fate. That fate was decided by the publication of this book, Galileo's Dialogo, published in 1632. Galileo studied medicine, mathematics, and philosophy. His early research was mainly on motion, particularly of falling bodies, but he became interested in astronomy and developed a new type of telescope. That, his observations, and his theoretical work on his observations led him to prove the theories of Copernicus, of which the Roman Catholic Church disapproved, declaring those theories blasphemous. Galileo ignored the Church's injunction against defending Copernican theory when he published this book. Or rather, Galileo tried to circumvent the Church's injunction by using a couple of tropic tricks. First, he proposed the validity of Copernican theory by setting his book up as a conversation, a dialogue. We're just hanging out talking. Second, he wrote the book in the vernacular, just talking Italian rather than Latin, the language of scholarly and religious written exchange. Of course, we know those ploys didn't work. Dialogo clearly affirmed the Copernican heliocentric theory over the Earth-centered Ptolemaic theory of the solar system. It was this book that brought Galileo before the Inquisition in 1633, less than a year after its publication. He was forced to recant his views and placed under permanent house arrest. His book was placed on the Index of Prohibited Books, where it remained until 1835. And here is an instance in which the power of multiple copies may be seen in near theatrical drama. 1,000 copies of this book had been printed, and the printing sold out before it was banned by the Pope a year later. And here is an instance where the power of the book and having a little library of one's own can be seen in even more dramatic fashion. This book, this physical object, should not exist. No copy of it should exist. It was banned. This is physical evidence of not following the rules. First, don't write it. But second, if it's written, don't own it. Did Descartes clip the wings of his own thinking process when learning of the trouble thinking caused Galileo? We can't know. We only know that when his book, Le Monde, was finally published posthumously, it was incomplete. But we do know that copies of Dialogo did not vanish. In fact, in Italy, where this book was published, a clandestine book trade took hold, and where scientific publishing programs might have ground to a halt, they instead went underground or got published elsewhere. England's Royal Society began underwriting foreign scientific works. For example, all the works of Marcello Malpighi, an Italian, including this work, were published by the Royal Society in England. This is the first published account of the systematic dissection of an insect, revealing painstaking work with a new tool, the microscope. It contains observations of the stages of silkworm growth, and it studies its organs. It influenced all sorts of observers. With the help of the Royal Society, Malpighi continued his work. He discovered pulmonary capillaries and alveoli. He argued that nature undertakes its great works in larger animals after a series of attempts in lower animals. The scientific community managed then, as it does now, to continue its work despite setbacks. Malpighi was served, if not in his own country, by Englishmen Henry Oldenburg and Robert Hooke, both secretaries of the Royal Society. For one thing, they furnished Malpighi with the most recently published technical literature. Oldenburg and Hooke solicited contributions from Malpighi and assured him of the good reception that his papers were receiving abroad. They provided him with encouragement and support. In fact, very much as Martin Luther had done during the first part of the 16th century, Galileo, Malpighi, and others could, for the most part, count on the support of numerous publishers, printers, and booksellers to keep up their work, rendering papal actions ineffective while making a profit for themselves. Dialogo was bought on the black market by priests and monks, as well as members of the secular community. Dialogo was a provocative and polemical treatise. Was Galileo deliberately courting censorship? Was the printer? Were the English deliberately undermining the Catholic Church by printing works the church banned? There's a lot of possible conspiracy here. In a letter, Malpighi wrote that a friend had mentioned there were advantages to having works condemned by Italian censors sail to England to be printed. We are nearing the end of another century. In 1687, Isaac Newton published his Principia Mathematica after the nudging of his friend Edmund Halley. We might imagine reclusive, weird Newton, self-sequestered in his own library, papers strewn all over the place, multiple experiments going on at one time. Newton, disheveled, plates of half-eaten food tossed to the side, and Halley cajoling, Zach, you've got to write this down. Halley flattered, bullied, and prevailed. This book is the culminating intellectual achievement of the scientific and print revolutions. Copernicus, Kepler, Galileo had shown the way by describing phenomena they observed. Newton explained the underlying universal laws of those phenomena. Newton invented his own brand of mathematics, calculus, just so he could do this. And he did not let us forget that. His theories ushered in a new age of discovery. It is likely that no more than 300 copies of Principia were printed. Halley couldn't get a printer to see the profit margin, and so paid for the printing himself. We have a copy, one of those 300, out there waiting for you to look at after the lecture. But just how engaged with this text and others were readers. Many surviving copies of books are in relatively pristine condition, suggesting that some owners did not study the text particularly closely. Our copy of the first edition of Dialogo is a pretty nice, clean copy, suggesting to me that someone just hid it under their mattress for centuries. But other copies tell a different story. Many surviving copies of scientific texts are richly annotated, and you will find examples of this on the books waiting for you outside. These readers read carefully and filled the margins with detailed notes. When an author died, colleagues were eager to buy his books, largely to have access to this marginalia. Sometimes annotations were transcribed from one copy to another. Newton dog-eared his own books in his personal library. The folds pointed to specific words and sentences, specific ideas. There is an anecdote that one librarian had fastidiously unfolded all of the dog ears found in a book from Newton's collection, only to discover later that the dog ears meant something. The librarian refolded the dog ears. Physicality means something, contains information in and of itself. Observation of actual objects means something. Books, physical objects, mean something. That's one reason we keep stuff. That's one reason the Marriott Library has the books that we're talking about tonight. And here we are, Newton having thrown, as Alexander Pope would later write, light upon nature, and nature's laws lay hid in night. By the 18th century, there's a whole lot of light. Someone had to try to collate all that light. Denis Diderot said that that was the purpose of his encyclopedia, to change the common way of thinking. The finest thinkers, the philosophes of 18th century France, contributed to Diderot's attempt to collate knowledge into something that was thorough, accurate, discoverable, and knowable. He asked Voltaire, Montesquieu, Rousseau, and others to write about what was known. Jean d'Alembert, the eminent mathematician, worked on this project with Diderot. The encyclopedists refused to accept the authority of political or religious power in questions of the intellect. They allowed nothing into the work that was not known through empirical study. The project was an immediate success. Large, expensive volumes accompanied by companion volumes of careful, accurate illustration were snapped up. Tout va bien, oui? No. The French royal court and the Catholic Church were outraged by the project and what it stood for. This was way too many guys hanging out on the street corner. In 1759, the 7 volumes that appeared to date were banned by the government and placed on the index by the Pope. For the next 20 years, Diderot carried on, writing countless articles while dealing with the attacks of critics and losing friends. It is hard to imagine such a substantial work as an underground publication, but that indeed was what it was, and it prevailed too. Very exciting. And yet, The articles in the Encyclopédie relayed in words the tools, the technology, the work in detailed literary and scientific terms. The 11 volumes of plates were meant to reproduce with scientific accuracy material reality. But if we look at these images beyond what the encyclopedists intended us to look at, the tools, the technology, we might notice that what they flatten almost out of existence are the workers. The emphasis is on the objects. Compare these neatly dressed workers in this absurdly clean pottery factory to the miners in the 1621 edition of Agricola's treatise on mining. First published in 1556, this work went through 7 editions before 1657, all of them retaining the nearly 300 woodcuts that correspond to the text. Perhaps the difference between the rather detached, if not barren, images from Diderot and the animated images from Agricola is that Agricola, like Fuchs and Vesalius, worked closely with their subjects. These woodcuts correspond with the text, depicting cutaway views of equipment and procedures used in mining above and below ground. They also depict the worker, so engaged with the equipment and the process that we get a sense of their very lives, from wiping the sweat off their brows, to women working alongside men, to children entertaining themselves with sharp picks while being watched over by their dads, to dogs lapping up water from a stream, to guys sitting on a bench in the middle of it all, talking. The Encyclopédie spatially separates the work of the mind from the work of the body, quite literally by separating the drawings from the essays, by producing them in a separate set of volumes. In the Enlightenment, artisans are not doing the work of the mind. In fact, although most certainly artisans discussed what they did and what they knew, their upperclassmen, so to speak, decided they could not understand what the artisans were saying. Their knowledge needed to be translated for the truly learned. The encyclopedists took Agricola's mines, Vesalius's surgical theater, Newton's littered lab, that is, applied and experimental science, out of the workshop, the field, so to speak, which had been applying and experimenting with practical sciences for centuries. The French philosophes, just before a great political revolution, nearly took scientific revolution down by almost removing people completely out of the manufacture of the product. If in the Renaissance science was to discover nature's nature in order to bend it to make human life more comfortable, Enlightenment science was particularly interested in the value of the trade that science prepared the way for, suggesting that the process itself was little more than a stage setting. And these are the guys slapping the wrists, if not the faces, of authority. The thinkers, the encyclopedists, are now the authority, not kings, not popes, not church hierarchy, and not workers. No wonder France had a revolution. Antoine Lavoisier, the man who laid the foundation for modern chemistry, was the unfortunate victim of that revolution. Before he lost his head, he carried out the earliest biochemical experiments, explaining many of the cyclical processes in animal and vegetable life. He reformed chemical nomenclature, assigning every substance a name based upon the elements of which it was composed. He proved that the increase in the weight of metals was due to something taken from the air, and that this effect was constant in all processes. He named this substance oxygen. He concluded that water was a compound of oxygen and hydrogen. With these things and so much more, he offered a new theory of chemistry, treated in a systematic approach unlike anything that had preceded it. Lavoisier's wife worked with him in his lab. A skilled artist, she provided the illustrations for Lavoisier's chemistry manual. Lavoisier partly funded his experiments by working in public service, reforming manufacturing processes of gunpowder and applying scientific principles to agriculture. He advocated for savings banks and insurance societies, public hygiene, and public education, all aimed at improving social conditions. But come the revolution, it was not enough. He was charged with tax fraud and selling adulterated tobacco. Mostly, he was not a revolutionary. His condemner is said to have said, "The Republic has no need for scientists." Print enabled the assessing and classifying of new knowledge and then distributing it to a worldwide audience. The speed at which this distribution happened was staggering in the grand scheme of human thought to this point. But information traveled in other ways as well, as it always had. Practical applications for technology traveled quickly and from point to point in the field of experimental science on the periphery of the book trade. In the 18th century, science was technology, was trade. Economics, not to mention politics, played a huge part in what was and wasn't discovered, devised, defined, demanded, and actually delivered. Local knowledge could become global science. In spite of powerful publishing companies centralized in a few large cities, craft and artisanship were part of the fine print. Standardization and dissemination became imperative for theory, but the doers, wherever they were and whatever they were doing, the experiments and the practical applications mattered. New information could be read and used in different ways by different people in different places for different reasons. And there was certainly reason to distrust. Printed works could be pirated and badly imitated, just as ancient works and manuscripts could be. John Flamsteed, an English astronomer and contemporary of Edmund Halley, who published his first star atlas in 1729, dismissed a posthumous printing of Tycho Brahe's star tables as a fraud. Sometimes information, no matter how well printed, illustrated, and documented, just doesn't add up. But the printing press made it easy to update information. When first published, Flamsteed's atlas represented a new era in celestial cartography, recording stars Flamsteed observed using equatorial and ecliptic coordinates. For the French edition, the size of the maps was reduced and the location of the stars fixed for 1780 instead of 1690, the date at which they had been initially fixed by Flamsteed. The editor added new discoveries by another astronomer. It was the same book, but it wasn't. It had changed with the times, just as the skies had changed. The smaller size made it less expensive and more practical as a handbook, something that could be carried rather than spread out on a table. Updated information requiring new editions of already published works, like software upgrades, and we all love those, were a necessary part of the presentation of scientific data as new material was added to data already gathered or as data became modified or even dismissed. Georges Cuvier was one of the most influential scientists in the 19th century. Cuvier's great work, Règne Animal, was first published in 1817 and translated and reeditioned many times. Cuvier was an anatomist and paleontologist. He classified animals into 4 branches, each sufficiently different from the other so as to disallow the possibility of any connection due to an evolutionary transformation, an infant theory to which he was opposed. For Cuvier, similarities in animals were due to common function, not common ancestry. Disappeared species were not a matter of internal change, but of external catastrophe. Cuvier did establish, as fact, the extinction of organisms, something that had been theorized by earlier scientists but not proven. Cuvier's work, his theories, observations, and his writings established a place from which to move. Not all of his theories or conclusions panned out. I suppose that we could say he missed the big boat, the evolutionary boat, the Beagle. But his work made possible a theory of evolution diametrically opposed to his own. Old information should be seen on an equal footing with any future transformation of the ideas that come from that information. It is all part of a set of modifications. In the future development of science, your science, the Founding Act, no matter how long ago it happened, may appear as little more than a particular instance of a more general phenomenon which unveils itself in the process. The Founding Act, the general phenomenon, the process will likely be marred by intuition and empirical bias, read in different ways by different people in different places for different reasons. Is this science we're talking about? Yeah, science. Reformulations, supplementary theoretical operations, establishing fact more and more rigorously over and over again. So much comes after the works we have looked at tonight. Michael Faraday's experiments with electricity, Charles Darwin's theory of evolution, Louis Pasteur's work with microbes, Marie Curie's research on radioactivity, Albert Einstein's theory of relativity, James Watson and Francis Crick's model of DNA. The printing press and its most substantial product, books, may be old-fashioned, but I hope these books have convinced you tonight that rules are made to follow, but also to break. I'm not suggesting you break the law, but break rules. Expect setbacks. Setbacks could mean you could lose your head, but don't give up. You can take the data to another country, from Italy to England, say, or the United States to Canada. Lab rats count too. Just because you don't become the dean of the College of Science, your work as a lab rat, a lab tech, a farmer, or a factory worker counts. All of us can observe, test, surmise. All of us can think, and all of us can do. Make it count. Be part of the crowdsource. Then and now, the printing and publishing of scientific works was and is expensive. Publishers will tell you that, certainly. Librarians will tell you that with tears in their eyes. Libraries and publishers are looking for ways to continue the dialogue, the conversation, in a manner that is discoverable and affordable. This will mean new technology, and we're not there yet. Whatever the new technology is that helps us continue the conversation, let's make sure that what we talk about now, what we think, why we think it, and how we present it now matters. Please, let's save it. What and how the past thought makes a difference to what and how we think now. What and how we think now will make a difference to future thinkers. Be pioneers, be revolutionaries, shake the world. And come hold your books.
Thank you, Louise. That was a wonderful lecture. Thank you so much. Now, there is one rule that if you break, you will lose your head. Because in a few minutes, we're going to let you go outside and look at 40 of these wonderful books. And if you go anywhere near them with food or Diet Coke, that's a rule you're not going to break. But for a few minutes here, I am sure Louise would be happy to take questions from the audience. And I ask you to speak loudly. Raise your hand and speak loudly, and maybe you could repeat
Sure.
the question. Okay.
Yeah. What was the greatest innovation in books and bookmaking before the printing press? What a great question. I happen to be a fan of medieval manuscripts, of handwriting things out. And I think that, I think it was the wheel, but that doesn't have to do with making books. I think there's something about writing things out by hand. I don't know if people do it much anymore. I did, kind of. I transcribed letters from a grandfather who served while he was serving in a war. And just that typing of the transcription was something I didn't expect. There was a kind of physical connection there to him that I just didn't expect to get in that way. So there's something, just like the physicality of books, there's something about the physicality of writing things out by hand that I think can connect us to whatever it is that we're writing or whoever it is that we're writing to or for. In the medieval manuscript era, early on in the Western world, it was monks who were writing out books, and that was done for the glory of God. And they felt a very prescient connection right there. So they wrote about it, they talked about it. So was that an innovation? No. I think it was the wheel that grinds the axes. Yeah.
Did books as pages evolve at the same time that the printing press did? I mean, was scrolls before that?
Oh, they are. Did books as books evolve with the printing press from scroll to codex? In the world of books, we call what looks like a book to us a codex. That is loose leaves bound at one end and covered on both sides with something to protect it, which we begin to make look pretty immediately almost. So that's the codex. That transition from scroll to codex happened in a long period that can be shortened maybe from between 200 BCE and 200 CE. And it went along actually with a change in the material that was being used for the support is what we call to write things down. And that was a change from papyrus to parchment, specially made prepared animal skin. By the time the printing press came along, the codex in Western Europe was the format. For most things, there's always exceptions. In history, there are always exceptions. But Gutenberg printed about 120 copies of the Bible. That was presumably his first major, anyway, printing project. And he printed about 40 of those on parchment, on the material that was what books were made of before this newfangled thing. So the material changes. He uses paper because parchment was really expensive. Paper wasn't cheap, but it was a lot cheaper than parchment. So he uses a new material along with this new technology. They kind of work hand in hand.
A couple of years ago, I was working on a paper on Lake Bonneville and found a book on Lake Bonneville by Carl Gilbert. This was the first publication of the U.S. Geological Survey under John Wesley Powell. It was just a treasure, beautifully illustrated. My concern was that as I was turning the pages, they were about to fall out. Do you have copies of these books that we can read without feeling so guilty?
A few. So there are some publications made in some periods of time that are much more hardy than others. These books that I have out for you tonight, most of them were printed before the before the 1860s. And the paper is really good paper. And then, yeah, paper becomes horrible. It's very cheap. In the 1850s, 1860s, people start adding wood pulp to paper, which is very acidic. And that was because of the war. That was because the world had lost a crop, and that was cotton. So paper got to be really bad, crumbly and fragile. And then in this country and in other countries, our government started putting standards on paper making so that it didn't disintegrate when you touched it. Like if you leave your newspaper on the porch, sunny porch, all day Sunday, you know what it looks like the next day. It's right. So there are differences in the quality of paper and bookmaking that go through the centuries, and it's good when you think it might be bad, and it's bad when you think it might be good, and then it's good again. And for those books that were made in the bad period, there are certainly things you can do to help preserve it, and we can scan things now. And we do that. Photocopying was hard on books, but scanning, overhead scanning, helps a lot. It still means you have to manipulate the book and shine light on it and do things to it, but it's very helpful in creating a copy that is readable, so you're not harming the book. Although I can't read a digital book yet. I'm not able to do it. But
There was a question. Let's take one last question, then we'll go outside.
You mentioned the threat to science of the church, which I was pretty much over, and the revolution, negotiating the resolution. What do you think is the biggest threat to the communication of science? That's a huge question. Of scientific knowledge right now, what would be your guess?
the question is, what do I think the biggest threat to scientific communication is right now? Given that I talked about, what did I talk about? No, church, yeah. Well, I'll just say it. I think government is problematic. I think governments can be can stop access of information, and I don't think, even though we're in the 21st century, we're in Banned Book Week right now, as a matter of fact. And I don't think that, which is something that libraries celebrate every year at this time. I don't think that is a threat that has gone away, that a government can attempt in some way or another, under the table or out in the open, to stop a free exchange of ideas.
Thank you. Fine answer.
Thanks.
Okay, thank you so much. I also, before we, hang on just one second, I also want to thank your staff for helping providing all these wonderful books out here. I want to thank staff from the College of Science, led by Paige Berg, I think she's outside, who does a wonderful job. There she is, putting this all together. And we'll thank Luis one more time. Thank you for a great lecture. Thank you for coming.